Okay, so in this second part, I want you to take some time to write down these two quick examples and then have the formula in front of you, the Laplace table. I just wrote a couple of formulas here so I can have them as a reference, but you can use your own Laplace table handout. So take a moment and pause and try to answer these two questions. This is again using the linearity property to find the Laplace transform, and then after that we're going to move on to finding the inverse Laplace, because as you'll see later, the inverse Laplace actually is the process that usually can be a little bit more tedious, and it may require some longer manipulation of the function in order to provide the answer. So after you just did that, let's check to see if you're right. So linearity property. By the way, try to do it in your mind whenever possible. So for example, this pulling up the constant and taking the Laplace of what's left and then distributing the Laplace transform. With a little bit of practice, you could do it in your mind just to make it more efficient. But for now, let's do it again with an intermediate step. So linearity property, that's the first thing to do, right? You distribute the Laplace operator and pull up the constants. So that 5 L of 1, and then minus 3 L of t, and then plus 7 L of sine of 2t. So notice that the idea is to end up with Laplace transforms of the entries in the table. I have L of 1 in the table, constant function 1, L of t to the n, so I have n equals 1 in this case, right, if you look at the formula in the table. And then 7L of sine of 2t. Be very careful with sine and cosine, because you need to identify what's the value of b, right? So I mean, in this case, sine of 2t means that in the table b is equal to 2. So when you apply the Laplace transform, obviously you're going to write 2, and then over on the bottom x squared plus 4. So once you identify these entries in the table, then of course you can write your answer. So 5L of 1 is 5 over s, and then minus 3 times L of t with n equals 1, that gives me 1 over s squared. And then finally plus 7, b equals 2, that's 2 over s squared plus 4. And then you can proceed and simplify it a little bit if you want. 5 over 3 minus 3 over s squared plus 14 over s squared plus 4. So that's the Laplace transform of the first function. Similarly, on the second example, 7 Laplace of e to the minus t plus 2 L of t third. Once again, read the table, and that should give me 7 over s plus 1, and then plus 2, n equals 3 factorial, which is 6 over s to the power 4. So that's 7 over s plus 1 plus 12 over s to the power 4. So this is how you take the direct Laplace transform. I'm going to isolate this section here on the table so I can write on top of it. And like I said, we're going to move on with some examples that deal with the inverse Laplace. So with the inverse Laplace, you may have to manipulate some constants. So let's actually illustrate with an example what goes on. So let's see, this is the third example. So let's say I need to find the inverse Laplace of the following. So let's say 5 over s plus 1, and then let's say minus 3 over s squared plus 4, and then plus 7 over s squared plus 1, and let's do another one, let's say minus 9 over s to the power 4. Okay, so the first thing to keep in mind here, especially on these three terms, you need to match it with the table and recognize the type of formula that you need to apply, and then see if you actually have the right constant multiplied by this entry. So if you look carefully, here I have 3 over s squared plus 4, and that will correspond to this entry in the table, right? You go from right to left. We have to find the inverse Laplace. This is b over s squared plus b squared. So pretty much any constant over a fraction like this, over a irreducible quadratic like this, s squared plus a positive number, is gonna tie it up to the sign of b of t. But the problem is that on the top you need to have precisely b, which is tied up to b squared. So in other words, if I have 4 on the bottom here, then you ought to have 2 on the top in order to match it with the formula. So once again, s squared plus 4 needs 2 on the top in order to match it with this formula. You don't have 2 on the top, doesn't matter, you can produce it, just make sure you don't change the original fraction. So you can multiply and divide by 2 the entire expression here. So you can multiply by 2 and divide by 2 the whole thing, because you could always pull up 3 over 2 outside of the fraction and isolate 2 over s squared plus 4, which matches the table. In the same manner here, let me see if I have actually room here, 9 over s squared, 9 over s to the power of 4. This is going to tied up to this formula, L of t to the n factorial over s to the n plus 1. Because I have s to the 4, that means for that formula n is equal to 3. Which means on the top you need 3 factorial, which is 6. 3 factorial is 6. You don't have 6 on the top, not a problem. You produce it by multiplying and dividing by 6 that fraction. So essentially you have to put the constant you need by legitimate algebraic manipulations. In other words, add and subtract the same thing. If you need to, in this case, multiply and divide by the same thing to produce the constant that you need. So with these modifications, now we can apply the linearity property, and here we can pull out 5. L inverse is of 1 over s plus 1, so that matches the table. Then here we pull out the constant 3 over 2 and leave inside 2 over s squared plus 4, which again matches the table now. S squared plus 1 is of the same type, requires 1 on the top. So here I just pull up 7 out of the inverse Laplace. And then finally on the last term here, I'm going to pull up 9 over 6. And I'm left with 6, which is nothing but 3 factorial over s to the 4. And that matches perfectly the formula over there in the table. So now we can use the table. And so this is going to be 5 e to the minus t. And minus 3 over 2 sine of 2t. This is 7 sine of t. And the last one here is 9 over 6, which can be simplified to 3 over 2. And 3 factorial over s to the 4 goes back into t third. So this is the type of manipulation you have to do. Unfortunately, there are even harder examples when you have to do even more algebra work. But I want to point out that whether you like it or not, it's unavoidable, because table of formulas will actually show you some standard functions. It cannot show you all combinations, because then you will have a table with, I don't know, millions of entries. So you need to have a way to basically break down your function into elementary entries in that table. Otherwise, it's of no use. So all it boils down is to handle these algebra tricks. Let me move on with one other quick example, and then after that we're going to deal with yet other situation in which you need actually to use partial fraction decomposition in order to match your Laplace, your functions to the Laplace table. So often when you have this quadratics at the bottom irreducible quadratics, the ones that cannot be factored, right? So s squared plus a positive number. Often you end up actually using both sine and cosine when you do the inverse Laplace. So here's a typical case when that happens. Let's see, that'll be the fourth example. So suppose you have to find the inverse Laplace of 7s minus 3, let's say over s squared plus 4. So you have to be very careful with the quantities like this, because they can be quite confusing, right? I mean, this fraction doesn't match anything in the table, but your starting point is always the denominator. If I have s squared plus a positive number, eventually you'll have to use these formulas, probably both in many cases. So notice the one that goes to cosine of bt has s on the top, and the other one has b, which is a constant. When you have both s and the constant on your numerator, you have to break down that fraction into two pieces. And then each piece eventually will match one of these formulas. So the first thing to do, via linearity property, actually we're going to do the linearity property later, but the first thing to do is to break this fraction into two pieces, 7s over s squared plus 4 minus 3 over s squared plus 4. If you have to, you may have to take this expression separately and manipulate it until it fits the table in a linear combination of the table. Okay, so let's focus on the first term. S over s squared plus 4 is going to match this perfectly. Okay, all I have to do is to pull 7 out when I use linearity property. So that's all here I need to do, just to move 7 out. On the other hand, just like in the previous example, this one needs 2 on the top, because this one goes with sine of bt. I don't have 2 on the top. I need to multiply just this second piece by 2 and divide by 2. Multiply and divide by the same thing, otherwise, again, you'll change the overall value of the fraction. So when you do that, of course, you're going to isolate 2 over s squared plus 4 when you do this linearity property. Now finally do the linearity property. So this is going to be 7 L inverse of s over s squared plus 4, and then minus 3 over 2 L inverse of 2 over s squared plus 4. And now we have everything in a linear combination that matches the table. So this is going to be now 7 cosine of 2t, there it is, minus 3 over 2 sine of 2t. And that's the Laplace transform of the original, the inverse Laplace of the original fraction. So before we move on to the second part, let's emphasize the situation in which you have to do, as I said before, the partial fraction decomposition. So that's another exercise that you have to do, or manipulations you have to do in order to match what you have in the table. I'm going to illustrate this with a very simple example, and then we'll move on to, in the last part of the lecture, with slightly more complicated examples. You will have to review the partial fraction decomposition that you used in Calculus 2. Same process works here, except you do it for s. So here's an example, which will be example 5. So suppose you need to find the inverse Laplace of 1 over s squared minus let's say 4s plus 3. So when you have a generic rational fraction like this, like that, you will notice immediately that it's not going to fit the table right away. Okay, so nothing on the table looks like that on the first look of it. So the solution in that case is always split it into partial fractions, because if you look carefully, the table of formulas contains formulas for all possible partial fractions? Well, the most usual ones, at least, of course. I mean, there are larger tables of Laplace transforms that contain all partial fractions. So the first thing to do is to see if you can factor the denominator. So let's take separately the fraction here. And notice that it can be factored into linear terms. In this case, it's s minus 1, s minus 3. Which means that eventually this will be a combination of these types of terms. Okay, but you have to find the split into terms like that. So that means you have to find the partial fraction decomposition, which, because all factors are linear, the partial fractions are of this form. There are two types of partial fractions. Remember, a constant over a linear term, or a linear term on the top and a quadratic, irreducible quadratic on the bottom. I will basically stick in this class only to partial fractions that are of this type, right? So I mean, this is the only type of partial fractions you're gonna see in our class. So how do you find the split? Well, you combine the fractions again on the left, on the right side, sorry. So you multiply this by s minus 3, and then multiply the second one by s minus 1. We can do this faster later with some shortcuts, but let's do it by the book so far. So then you collect the terms by the powers of s. So as plus bs combine into a plus bs. And then you're going to have the constant term, which in this case is minus 3a minus b. Then you're going to end up with a system in a and b. You match the coefficients from left to right. Since there is no s on the left side, you can think of the left side as 0 times s plus 1. So since there is no s on the left, that means a plus b must be 0. And then the constant term minus 3a minus b must be equal to 1, the constant on the left. So you solve this system by elimination. So if you add the 2, b will cancel, so you end up with minus 2a equals 1, and a is going to be minus 1 over 2. And from the first equation here, if you plug in a, you get b 1 over 2. So once your partial fraction decomposition is established, then use it in the inverse Laplace, and then use linearity property. So your fraction here ends up being equal to minus 1/2 1 over s minus 1 plus 1/2 1 over s minus 3. And now you can use linearity property, minus 1/2 L inverse of 1 over s minus 1 plus 1/2 L inverse of 1 over s minus 3. And then of course now we can use the table. That's going to be minus 1/2 e to the t plus 1/2 e to the 3t. And that's the answer. So I'm going to show you later a shortcut on how to do this a little bit faster. You'll see it can be done faster, but for now, make sure you remember how to do this partial fraction decomposition. And I'll show you an example in the last part of the lecture when you have, different types of partial fractions, like this one and the one with the quadratic format. So stay tuned for the next part. I'll see you soon.